All right, so I had to show Izzy. This is my setup. She has to check it out, make sure everything's okay. Izzy, you look up here. Hey, Izzy. There we are. Say hi to everybody. Izzy, can you say hi? You're purring. Hey, look up here. Okay. Okay, that's good. Thank you. Thank you, Izzy. All right, down you go. You're welcome. All right. She bumped the camera too bad? She didn't bump it too bad. That was kind of funny. All right. Okay, I think we're good. Figured you guys needed a little break there. Okay, so we just talked about units of pressure. Pascal is a Newton per meter squared. Another unit of pressure that we'll use is the PSI. That is pounds force per square inch. That is the English unit that we will typically use in this course. Another unit that we will use from time to time is the atmosphere. 1 atmosphere, and I don't know the exact value, but it's roughly about 101.3 kilopascals. Okay, so it's a little more than 100,000 pascals. It's also about 14.7, that's not exact, but that's close, psi. 1 atmosphere is the pressure that the air exerts on your body, or anybody, at approximately sea level and approximately room temperature, so we'll say about 70 degrees Fahrenheit, or what, 20, I don't know, 25, something like that, degrees Celsius. I don't think in Celsius, I have to do the conversion quickly. So that is 1 standard atmosphere. Now, you will see from time to time the bar. 1 bar is exactly 100 kilopascals. So 1 atmosphere is approximately 100 kilopascals. 1 bar is exactly 100 kilopascals. This is approximately an atmosphere. Here in where we're at, kind of in the central part of the country in the United States, we're a little higher than sea level here, not by much, but a little bit higher than sea level. So we would actually be at a little lower pressure. We probably won't be all the way at 101 kilopascals. We might be closer to a bar here where we're at. Okay. All right. So the next thing we're going to talk about, that's where we talk about units. I do need to define a couple of things here, and I should have grabbed my tire gauge out of the car to show you, but that's okay. So there's this quantity we call a gauge pressure. A gauge pressure is the difference between absolute and atmospheric pressure. Now, why is that helpful? Well, let's say that I go out to my car and I measure, I'm going to take my gauge and I put my pressure gauge on here, and it gives me a gauge reading of, I don't know, let's say 30 psi, 30 pounds force per square inch. That's a gauge reading. And that's a gauge reading. So here's the question: what is it telling me if I go out to my car and I put my gauge on my tire and I get a reading of 0? What does that mean? A reading of 0, a gauge reading of 0. Does that mean there's no air in the tire? No, it doesn't mean there's no air in the tire. That just means, it means one of two things. Either my gauge is broken. We want to make sure that's not the case. If you hear a hiss, it's probably your gauge is broken. But if you don't hear a hiss and you're getting a 0 reading and your tire looks flat, it's probably because the pressure inside, the absolute pressure inside the tire, is the same as the pressure outside the tire. There's no difference. A gauge is typically going to measure the difference between the pressure inside your measurement and the pressure outside of your measurement. So when you get a gauge and it gives you a reading, understand that that's not the actual pressure inside. The absolute pressure inside my tire would be the gauge pressure plus the atmospheric pressure. And again, remember here, 1 atmosphere is typically about 14.7, so if the gauge pressure is 30, then the absolute pressure inside my tire is actually about 45. It's 14.7 plus 30, so that's 34.7. So just be aware of that. If you get a gauge reading, that's not the actual pressure. This absolute pressure could then go into ideal gas law. Right? Don't put the gauge pressure into ideal gas law. You have to put the absolute pressure in ideal gas law. Just like you wouldn't put a gauge, a relative temperature like Celsius or Fahrenheit into ideal gas law. I can't put a gauge pressure into ideal gas law. I have to put an absolute pressure. Okay. You will sometimes be given a vacuum value. That is the opposite of gauge. What that means is if I have a device that's designed to measure a vacuum, then rather than report a negative gauge pressure, what it's going to do is it's going to give you a vacuum value, and that just tells you how much the pressure inside is below the pressure of the atmosphere outside. So if you encounter a pressure gauge that has written across the gauge, the face of the gauge that says vacuum, what they're telling you is this is going to give you this measurement. Okay. So just keep that in mind. We won't encounter that very often. If you have a complete vacuum, if you have something that's a complete vacuum, that just means the pressure, the absolute pressure is 0 if you have a total vacuum. Okay. All right, L1 and 2. This is page 4 of my notes. That kind of keeps me straight. So when I'm looking through these later, if somebody has a question, I'm like, what the heck was that? I know where to look at least. All right, what else? Here's where we talk about pressure change within a column of fluid. So again, let me finish writing before I try to talk. So again, if this is a face-to-face class, I'm just using my PowerPoint slides I would use in my face-to-face class because they kind of keep me on track and I don't go too scatterbrained. If we were in class, I'd have these on a smart board and I could write stuff on here, stuff like this on here, but we're not. Here we are, so that's okay. We'll make do, right? Hopefully these are helpful. Pressure change within a column of fluid. So think about this. If I go diving, right? If I go swimming and I go swimming under the water, or I go diving under the water, we know as I move down, pressure increases with depth. Correct? Right? We know that. I think we're all comfortable with that. As I move down into a fluid, I'm going to experience more and more pressure. Now, if I want to know mathematically, how much does that pressure increase? Well, we can quantify that. We just got to use some physics. And if you've had statics, that helps, but if you've not had statics, we should be able to just rely on what you know from physics. Now, I'm going to work this in 3 dimensions. And I know you maybe haven't seen a lot of 3 dimensions in your physics class, unless you've had statics already, and that's okay. Just kind of, I'm going to go pretty... I'm not going to expect you to do this derivation, okay? I'm going to derive this down to a simple equation that we're going to be able to use, okay? Now, if I look at a free body diagram of a cube of fluid. So let's draw a free body diagram of a cube of fluid within this column of fluid. Okay, so I've got a big column of fluid here, and let's say I grab just a little tiny cube within this column of fluid, and I want to know what is the pressure change within that column of fluid. And it could be any column of fluid, but let's say we've just got an arbitrary column of fluid. The x direction is coming into and out of the page, the y direction is left to right, and the z direction is vertical. And so we'll just say this cube has dimensions x, y. I know that y is probably a little small. We'll say this cube has dimensions of x, y, and z. This is how I draw my z. Okay, if we look at the forces, because this is a free body diagram, we want to look at all the forces applied to this cube. Well, I've got on top, I've got pressure, let's say P1. Now, pressure is not a force. pressure is force per area, so to get a force, I need to multiply by the area of that face. So this top face has dimensions x, y. So the force applied to this top face is P1 times x times y. So pressure times the area, that gives me the force. And pushing up from the bottom, again, pressure always pushes, and it pushes perpendicular to or normal to the face it comes in contact with. So this bottom face underneath the box also has dimensions x, y, and so it has P2 pushing down there at the bottom times x, y. We know P2 is bigger than P1 because we know pressure increases with depth. This is deeper, so P2 is higher. We don't know how much higher. That's what we're trying to figure out. Okay, and then if we look at the other force, there's also the weight. There's the weight of this cube of fluid. Those are the z direction forces, the up and down forces. Now let's talk about the left to right forces. So I've got a force here and a force there. What are these forces? These are the side pressures. Now I don't know the side pressure. It turns out it's just the average between 1 and 2, but we don't necessarily know that. So let's just say P side and P side. I've got no reason to believe that they're anything but the same, right? So if I assume that they're the same, pushing on the sides, and again, that's not a force, it's pushing on a face. That's this pressure, and this face has length x, height z. So this is x, z. And the same thing over here. This is pushing on a face, x, z. So I've got the pressure pushing on the side, there and here, left and right, pushing on faces with areas x and z, and then into and out of the page, the x direction. I also have a side pressure here, and that's pushing on a face that has dimensions y and height z. So this is y, z, that is the area of that face. This pressure times that area gives me a force. And pushing out of the page, basically, kind of in the positive x direction, this is also P side times y, z. Alright, so if I do my statics or I do my physics here, physics says, Newton's second law says, let's not do a particular direction, let's just do a vector. Newton's second law says if I add up all the forces, and if this thing is not accelerating, all those forces have to be zero. A body at rest tends to stay at rest unless acted upon by an outside force. This is Newton's laws. Okay, we should learn that in physics. Now, again, I'm writing it in vector form. You may not have worked this in vector form in physics, and that's okay. Let's talk about the x direction forces. So in the positive x direction, this one's coming out. This is P side times yz. That's positive, so I'll just leave it. No sign on that. But this one's going into the page. That's the negative x direction. So this is minus P side yz. Now those are both in what we call the x direction. I'm going to put an I vector on that to denote that's the x direction. Notice these are the same. This is equal and opposite. This is just going to be 0. And that's okay. In the y direction, that's left to right. So in the positive y direction going to the right, that is P side times x, y. And in the negative x direction, the negative y direction, that's going to the left here, also P side, and that's xz, I apologize. That's xz, and this is xz, and these are in the j direction. And then last but not least, the z direction, the k direction. Depending on what you've done with vectors, maybe this is new to you, and I apologize, but I don't expect you to do I, j, and k vectors throughout the semester. This is the only time we'll see them. So just understand this is x direction, this is y direction, and let's work in the z direction. That's up and down. So going up, I've got P2 times xy. Going down in the negative z direction, I've got the weight, and I've also got P1 times xy. Again, these are all in the z direction, which we can represent with a k vector. Now, again, if we add all these up, we should expect 0. There's no, if this is not accelerating, we should expect 0 force, sum, total force. There is this minus that is 0. So there's 0 in the x direction, 0 in the y direction, because again, this is this minus that. And in the z direction, I've got T2. Okay, let me finish this